Friends, it's my honor and privilege to introduce my guru, Dr. P.S. Balaji, who is going to deliver a lecture on advancements in additive manufacturing for mechanical engineering applications. So, Dr. Balaji P.S. is an assistant professor in the Department of Mechanical Engineering at National Institute of Technology, Rourkela. He earned his PhD in vibration control from Curtin University, Australia in 2017. With over 8 years of teaching experience and research experience, Dr. Balaji specializes in non-linear vibration control systems, passive vibration control devices, vibration energy harvesting, and advanced machining process. His research contributions include 26 plus SAI publications and leadership in 3 sponsored and consultancy projects. Dr. Balaji has also guided 2 doctoral students and coordinated 10 continuing education programs, reflecting his commitment to advancing mechanical engineering education and research. I welcome you, sir.
Okay. Thank you, Dr. Bhargav. Shall I share my screen?
Yes, sir, please.
Okay. Is my screen visible?
Yes, sir, it is. It is visible.
Okay. Okay. I'll start my talk.
Okay.
Okay. Good evening, participants. Thank you. First of all, I'd like to thank QIS College for giving me this opportunity to share some of the research insights and some advancements what I can discuss in additive manufacturing. So in this presentation, we would be majorly starting from what is additive manufacturing, and we'll slowly move on to the topic which says what are the advancements possible. First thing is, since we are talking about manufacturing and especially on additive manufacturing, we cannot directly jump into the additive manufacturing. We should actually start from the word manufacturing. So if you see in general terms, manufacturing is defined as a process of converting raw material into finished product. In that way, you added a value and utility. The raw material cannot have some value and utility. By converting it into a product, you are adding value and utility. Such process of conversion is manufacturing. So now, in this process, we have to design what is the product we want, what kind of material we want, what is the shape we want, how to join them if they are multiple one, and how to assemble and inspect all involves here. In fact, I can say in that way, manufacturing is the backbone of any economy since it transforms idea into tangible product. Especially if you take a country like a China, they are highly developed in manufacturing. If you take country like our own country, which is India, we lack such high level manufacturing facilities. See, we can make a raw material. We are having lot of mines like coal mine. We have a steel, iron ore mine. We have zinc mine. From there, we are creating the raw material. But raw material may not have the high value to it until we convert that and extract the material. So what we do is we are selling the raw material directly in a very low cost to the countries which can manufacture, which has a very good manufacturing facility. So they buy our raw material and convert it into value and selling it for higher cost. So then you see we are the one who's supplying the raw material, but finally what is the profit we are getting? Very less because we are selling the raw material but not the finished product. So this makes a very clear understanding that manufacturing is actually backbone of an economy. If you break the backbone, the entire economics collapses. Now we need to understand why from manufacturing we have moved to additive manufacturing. What are the reasons that have pushed us? So in that way, we can start that the points are visible here. Like one first most is the need for higher production. Higher production in the sense the mass production. when you are trying to develop a new product and bring it to market, and as soon as the commercial benefit starts, then many people wants to buy, so you need to produce them quickly. Second one is advancement in tools and material. If the new material is coming into market that have higher strength, then the tool that needs to give the shape needs to also have higher strength. So advancement has led. And secondly, labor cost reduction. The cost of the product also covers the labor cost. So if in the place of 10 laborers, if 5 can work, then the labor cost is reduced. And quality and precision and digital transformation sustainability goals are the reasons that is pushing us from simple manufacturing into some advanced manufacturing concept. If you see how manufacturing started evolving, see, when you talk about the Stone Age, where people have made the weapons that were used to hunt animals, they used the manual method to cut the stones into a sharp object. Now, using the sharp object, they were able to hunt, eat, and enjoy the food. But sometimes the stones are very heavy and having high strength, so they could not manually do. So they started inventing some mechanical tools to cut the machine. So now from the transition of manual into some machine happened. From machine, what happened is they thought, why I have to machine it manually when I can convert into an automated by incorporating a CNC program. So from manual, it went into mechanical related, that's mechanized. From mechanized, it is getting into automated. So now CNC programmings are happening. On an overview of this step so far, it might look like we went from manual into automated, so my job is done. No. Later, the world transformed from automated into digital. See what happened in the mechanized one, I have to use my drawings which are made in the paper. So, for example, the engineering drawings, what we are teaching to students, that is just to make them prepared to make the CAD drawings that are needed for the design. But nowadays, nobody, I cannot say nobody, it's very minute people are using the drawings in hard copy. Majority are using the drawings in the soft copy, and nobody is drawing the drawings. They are only making the drawings from the CAD softwares like CAT or SolidWorks. So once the product is ready, you can even check them by using some simulation. So that gives a digital form of an object. So from mechanically making into physically making the product or design into automated, we have reached. So it might look like we have completed the circle from manual to digital, but no. The later came the advancements called additive manufacturing. See how this additive manufacturing is helping us. We will be seeing in the coming slide. But you need to understand from the manual, we went into mechanized, then we went into automated, then digital, and finally we are in the life of an additive manufacturing stage. I can even give a guarantee right now. We can mark my words and you refer it after 20 years from today. How every house is having a TV, washing machine, or a grinder, or whatever, they will also have the 3D printer. A small scale 3D printer would become every household's activity. For example, you need a mug. You don't have to go to shop and buy. Instead, you can print the 3D mug. And your pen cap is lost. No need to throw the pen. You can print the cap of your pen. Okay, so your watch strap is broken. You can design and you can build your own watch strap and put it to your watch. So such great things are possible in the additive manufacturing. So what will going to happen in coming years is in the homes of the public, we will also have a 3D printer, and that would become part of the household appliances. So when I talk in terms of manufacturing, there are only three ways in which I can manufacture the product. Okay, three ways. The first method is subtractive. Subtractive means what? I take a raw material, the billet, okay, billet, I call the billet technically in terms. Then I remove the unwanted portion of the material to get my shape. So they are all coming under the concept called a subtractive techniques like milling and drilling. What I am doing in milling, I am taking one block, for example, lathe machine. If I want to make a step shaft, I will take a shaft which is very complete. Then I slowly remove some diameter of the shaft until my desired diameter is reached. So such process are called subtractive. So once you overcut, for example, instead of a 10 mm, you cut a very deep of 11 mm, then there is no control. Is that possible? Because what already subtracted is already gone forever. So these are all concerned subtractive. The second technique is called as formative. Formative in the sense that giving shape to the billet. Say one of the very easiest way to understand formative is our roti what we are making at home. Say we are having a roti. When we are making a roti to make it flat, we first make a solid spherical shape. That is the material we are having, and then we use the pressing things to make it flat and round to make our roti. So the shape is given to the definite volume of material. So such formation is called as formative, which means I'm forming a shape from the given input. So first case is about subtracting the material. Second case is about forming the material from the given shape. And the last third is additive. See, when I have a subtractive, when I have a giving shape, the last and advanced topic called additive. See, in additive, what we are doing is instead of removing the unwanted shape of the material, I am only creating the wanted shape. If I want a specific shape, I will be building the material layer by layer. Even in coming days, the 3D print comes under the concept called additive manufacturing. So the word add, additive, the word add always indirectly says that we are going to add some portion of the material. So these are the three major ways in which the entire manufacturing field is settled. What are the ways? Subtractive, formative, and additive. Now, why additive manufacturing started coming? What is the need? If you see the traditional process, for example, the casting, the turning, the milling can satisfy our need, we would have not went to additive manufacturing. But still we went to additive manufacturing because the traditional process are efficient, but we don't have the design freedom. For example, I want to make a spherical shape, but inside spherical shape, some design has to be incorporated. It is not possible in a traditional process. But I can do any complicated shape and sizes in additive manufacturing. So the need is pushing me towards a new technique. However, additive manufacturing is slower, but the designs it can make is unlimited. It is not limited by any kind of, I can say, geometry. You can make the geometry any complex one. You can make geometry which are simple. But I wanted to say one thing. If we are having option between choosing additive manufacturing and choosing traditional, what you should choose first? See, there is no need to even think twice. If your traditional method can satisfy your need, please go ahead for traditional methods like milling, drilling is absolutely fine. You can move to additive manufacturing only when your traditional and conventional method fails. Why? Because additive manufacturing will give you a final product, but the strength of the product is not as good as traditional process. But you get some product which is not possible in traditional. So that is the added advantage. So now another major use of additive manufacturing is I can convert a CAD directly into a print without need to a manual input. I design a model, then directly I send it to the computer to print. Second is rapid prototyping is possible, which means that once I design, if a design is in your brain, how to explain it to the other people? Immediately I'll make a design, immediately print. So showing is much easier than explaining in words. And third is lightweight and optimized. Yeah, this particular means that if the weight has to be optimized, if you want to reduce the lightweight, all are possible in CAD model. So when the model is directly sent to computer for printing, so your model will also lightweight optimized and waste minimization and sustainability goals. Here we are only creating the wanted material, which means unwanted space we are not even creating. In the sense, the wastage is very much minimum. At the same time, you can have a filament which can be printed in any shape, any size as per the requirement. If I get a requirement, I will print. So I will only keep the raw material with me, not the complete product. So these are the advantages which is pushing me from the traditional method into my additive manufacturing technique. Now, how the additive manufacturing started evolving? It is 2025. You have to go just 40 years back. So the foundation of additive manufacturing started in the year 1981 in Japan. And when the additive manufacturing was proposed in the early stages, people could not even understand what is this additive manufacturing. They were called it as rapid prototyping. How rapid prototyping is becoming additive manufacturing means the rapid prototyping is a concept that you need to make a small scale model of your design so that others can understand the design. But in order to make the small scale model, I have to go to a manufacturer and explain my design. But instead, I will have my own manufacturing system that is a 3D printer which will design my prototype so I can show to people. That's why the name rapid prototype started coming into it. The rapid prototype is quickly you can make the prototype so that others can understand. Later, slowly, the improvements have driven until the year 2025. The rapid prototyping or 3D printing has become so advanced and so mature technology that even a school kid, once he understands how to use rapid 3D printing machine, it is possible. So now since all along the presentation, we are going to focus on additive manufacturing. We started from what is manufacturing, then we went on to the what are the three major paradigm that is subtractive, formative, and additive. So the additive manufacturing lies on the third method. From that additive manufacturing, we saw what is the need for making additive manufacturing. Now we are coming to the actual process called additive manufacturing. So what are the step by step involved in additive manufacturing? Of course, the first thing that is involved is having a CAD model. This CAD model can be made in any software like SolidWorks or CATIA. So many CAD models are available. The first job is what is in your mind, you need to put it in the model. Once you make a model, then you need to convert the model into .stl file, that is standard tessellation language, because we are having a 3D printer and CAD model is having a software like SolidWorks or CATIA. They make the model in a very specific format. This format has to be converted into 3D printable format. The .stl format we have to convert. How to convert? It's very easy. It is so easy like converting a Word file into a PDF. Just go to File, Save As, select the format and give a name. Boom, done. So converting into STL is the next step. Now we have a model in a computer converted into .stl file in the computer. What is the next step? Now we need to import that model into a 3D printing software. So once I import the model into 3D printing software, the first thing it will do is it will do slicing. Because you see, in 3D printing, we are going to develop the entire 3D print in layer by layer manner. Any kind of 3D printing you take, we will be seeing what are the types and what are the advancements made, but all makes it in common way like layer by layer. Once layer by layer is done, Then I have to feed the material into my 3D printer. So far, the first three steps, CAD modeling, file conversion, slicing, deals with the softer part of the machine. CAD model, I will do it in my computer. File conversion, I will do it in my computer. Slicing, I will do it in the computer in which 3D printing software is involved. Now I'll go to 3D printer and give the filament or powder or resin depending on what kind of 3D printing machine. So now for the fourth step, I'm coming into machine. So once machine is done, then it starts printing layer by layer in whatever method that 3D print depends, it will make. Once the layer by layer is done, then you do a post processing. Then finally, once the post processing, in the sense you will remove the completed part and then you do a quality inspection, boom, your product is ready. So these are the major steps in any kind of 3D printing possible. Now you have to understand where a 3D printing can be improved. At the same time, you also have to think how, nowadays the entire world is worrying about AI. AI in this, AI in that, AI everywhere. So 3D printing is also not immune to this AI craze. In 3D print also AI is involved. So when AI is involved here, where it could be involved, you can think whether it is involved in CAD modeling or file conversion or slicing or material feeding, you keep thinking about where AI could be involved. In the coming slides, we will see what are the possible ways AI is currently used. Okay. So now let's go to the core and technical concept of a general 3D printing. 3D printing. The general 3D printing, what it does is it takes a cross section of the 3D model. For example, I want to print a cylinder. Cross section of a cylinder is a circle. So I'm going to print circle by circle by circle by circle until my required thickness of the length of the cylinder is needed. So the 3D printing basic concept is it looks at the cross section of the model. Then once the cross section is identified, the material is deposited or solidified using thermal, chemical, or light energy. Any of the energies are used. So it depends on what kind of 3D printer I'm using. For example, if I'm using a fusion FDM, like fusion deposition modeling, I'm using a thermal method to deposit and solidify. If I'm using SLA, I'm using some chemical. If I'm using photo-sensitive material, then light energy is also used. And last one is bonded layer by layer by melting, curing, or additive. See, once I make layer on top of the each layer, there is a very specific thing I have to take care. Because once I make one layer, then the layer is wet because just now I made. Now I'm going to make one more layer on top of the given layer. Now the problem is when the first layer is still soft and wet, then I put one more layer on top of it. What will happen? My first layer will collapse. But that should not happen. For 3D printing, we have to maintain the time in such a manner the first layer should get solidified, but it should not solidify so much that when I put my second layer, then they don't stick to each other. So I have to put my first layer, then it has to solidify some, and it's still some liquid portion should be left. Then on top of it, I should put my second layer. So people have already did lot of research and optimized the complete 3D printing process. So now you don't have to worry. So the core concept of uh, 3D print is like identifying the cross section, depositing and solidifying each layer, and finally make sure that each layer sticks to each other. Boom, the 3D printing is done. So I can call analogy like 3D print is nothing but printing a book one page at a time, but in 3D. So you are have to print a book, you are printing page by page, and finally you get a product. So this is the best example to understand how 3D printing works. Now, what are the general parts of a 3D printer? Say, the figure on your left side shows a complete product what 3D printer can make for you. Now, the question what you can raise in your research or in your idea in your mind is, This 3D printer looks very easy and very simple. So can I make my own 3D printer? Yes, possible. You can make your own 3D printer. The only complication will come is you need to make your own G code so that the movement of the nozzle can be programmed as per the cross section. If you are still struggling, don't worry. In Amazon, you can even get the simple 3D printer for 25,000. So whatever 3D printer, whether you buy for 25,000 or you buy for 3 lakh, the parts of a general 3D printer remain same. For example, what kind of 3D printer we are showing is FDM. There will be a filament which starts from the top. So that is a material that is going inside. And then you have extruded because filament is a thin solid. I want to melt it. The melt happens in the extruder. Okay, the extruder also pulls the material and feeds into the hot. It's not. It's called hot end. So in hot end, there is a nozzle that is eating the filament and making it liquid, not exact liquid, semi-solid. Then you have print bed, and finally there is a LCD screen to control the parameters of a 3D printer. Now, during a 3D print, the nozzle will be very much close to the print bed so that printing will start happening. Okay, so filament, extruder, hot end, print bed, and LCD screen are the very general parts. Now, still again, you have to think what kind of advancements and where A is incorporated. You keep thinking about it. We'll come to the part later in the slide. And now, what kind of materials I can print? Can I print all the materials? The answer is simple, no. You can only print certain materials. For example, you can print polymer. Common examples are ABS, PLA, nylon, PEG, PEG polycarbonate. These are the materials generally we use. Even TPG also we use. TPU, it is TPU we use. So they are used for prototyping tools, function. In polymer, the problem is they are very kind of plastic, I can say in layman language. So majorly I can use them for display purpose only. Structural purpose, polymers may not have great strength. So they went into metal-based 3D printers. Metal-based 3D printer can print material like titanium, stainless steel, aluminum, inconel, cobalt, so many process, but they are metal, so they have good strength, so they are useful even in aerospace one. And ceramic and composite also possible like silica, alumina. If you have ceramic based 3D printers are also possible, so they are using high temperature and very specific going. There are even other materials like bio. See, nowadays you are getting a 3D printed food. See, 3D printed material used for mechanical or aerospace is still understandable, but in future, 3D printers also will part of the kitchen, but they are specific kind of 3D printed. They print food. For example, you want a burger, you don't have to make the burger. Instead, you can 3D print a burger. Okay, so 3D printers can also become part of your kitchen also. The days are not very long. It is coming. Now, how the 3D printer performance is compared with the conventional? The first is material use. If you talk from material use point of view, 3D printer uses only required portion of the material. So I can say minimal waste. You can ask, sir, if you are only you are printing a required portion, where the waste is actually coming. Because when I do a 3D print, I have to create some support structures for my 3D printer, which after the print of the material, they are waste only. So what are support structures? We will see little deeper, which are not covered here. But support structures are like when I print a material or product which are very lengthy, then I need to also give some support so that those parts don't fall down. But once the 3D printer is done, the support structure can be removed. So they are waste, but they are very minimal compared to the waste created by the conventional process. Second is in terms of design. There is no limitation. You can design anything. For example, a sphere, having a sphere inside and having another sphere inside that sphere. This is not possible in conventional, but possible in additive manufacturing. And next is tools requirement. If I want to use casting or forging, I need to have a die first, and then I have to have a mold and cutter. But when talk about additive manufacturing, one machine for all shape and size. Of course, 3D printer comes with a limitation of how much it can print. Within that, you can print anything. And lead time is very long, which means that what is a lead time? The day from which the component is designed and the day in which finally the output product is made. If you take conventional, if I make some design, I have to make the tools, dies, and molds. So finally, the time taken to convert the design into product is very long. But if it is 3D printer, directly design, go to 3D printer and print it immediately. So lead time is very much short. Of course, the time will be taken for printing the material, that is 8 hours, 10 hours, depending on complexity. But it compares with the conventional where I have to first make the die, make the tools. So lead time is very short in the sense. And second is economy. Conventional is good for mass production, but additive manufacturing is good for customization. For example, customization in the sense I want to print a coffee mug, but on each mug I want to write a name of somebody. Then I have to make a specific conventional dies and molds for that. But once I made, I can make them mass production, but I want to make only once, then it's not suitable, right? So that I can use to additive manufacturing. And repair and modification is very easy because the portion which got broken, I can print again on top of it. But conventional little difficult. Complexity increases with the design or cost, but it is independent. Whatever you make it, it is possible. And now you have to understand when I have to, if you are going to a shop and you say, you please do a 3D print of this material, the charge is whatever the person is asking, not on the design, not on the complexity of the design. Why? Because 3D printer is going to print. So you charge only based on time taken to print and amount of material needed to print. So your payment is done on the volume of the material, not on the design. If the design is simple or complex in whatever sense, doesn't matter. Only amount of material that is used. So please understand, when you are trying to print anything outside from any company, you only make sure the charges are based on volume of the material. Okay. Now, when I'm 3D printing, what are the parameters that are influencing? We will just say some parameters. So when you understand how the parameters are coming, so the advancements can be made understand very easy. First is the layer thickness. Since I'm printing layer by layer, so the thickness of the layer affects the surface finish and the quality of the material. Second is build orientation. For example, a cylinder, I can print circle by circle in a complete vertical direction, or from the along the length it is a rectangle by rectangle. So I can print rectangle above rectangle also. But it's a very common sense that circle by circle, if I print a cylinder, it is better. So the build orientation has to be decided in what way you want to build, because the build orientation is also going to affect the strength. Always understand the layer, it is better to have along the loading direction. If layer length is 90 degree to loading, then your material will fail. Better to have the layers along the loading direction. Second is speed at which you want to print. You can even print the material very fast or very slow. But if you print very fast, then layer by layer, time won't be available to adhesive stick together, so material will fail. And second is cooling rate. You know already from annealing process what we follow. If you cool them very quickly, they become brittle, because the cooling also affects the microstructure. But in 3D print, it has to be cooled in certain rate so that the 3D layer by layer can be made. So this cooling rate also will decide the microstructural behavior. Finally, the one important thing is infill density.
Infill density in the sense, if I want to make a cylinder, can I make only the outside skin of a cylinder, or the inside also it should have a material? So that becomes the infill density. If I don't need inside material, I can only create outside skin. That depends upon the application where I have to use it to only showcase. So I will only print the outside shell. But if I want to use the cylinder for some application which should have some strength, then I'll fill the inside of the material also, so that the strength can be given. So that control is with you, how much you want to fill inside. So these are the very major design parameters: layer thickness, build orientation, laser power, cooling rate, and infill density. So now, what are the advantages of additive manufacturing?
Because we are all thinking about additive manufacturing, and we even compared it with the conventional on specific parameter. The advances is that you know already now design flexibility, because your design does not now affected material efficiency, because any shape you can make. Customization, of course, you can definitely make. Rapid prototyping, very good. Lightweight, on-demand manufacturing, and integration. So all the advantages makes you feel like, let's scrap all the manufacturing process, let everybody shift to additive manufacturing. No, that is not possible, because they also have some limitations. What are the limitation is slow build up rate, which means that to make a product it takes lot of time, and limited build size, which means that the size of the product depends upon size of the 3D printer. Surface roughness issue, because the layer thickness affects surface roughness. And anisotropic material property, because the layer direction also defines the material property. Definitely post processing is required, and high cost for metal system. For example, a simple lathe machine cost and a metal 3D printer cost, if you compare, it's very clearly visible. Metal 3D printers are much, much, much costlier, like 3, 4 times of your lathe machine. Okay, so the 3D printed metal printers are costing around 1 crore, 2 crore, and 3 crore. They are all in crores. They have not even come down to lakhs. Only the 3D printer which you are using the polymer, they are coming in lakhs. So now, what are the errors? So if I make a material, will it be 100% error proof? No. There are certain errors are there. One is like porosity. Porosity in the sense the material may not be completely solid. Some air pockets are possible. Wrapping, because of the sudden cooling and sudden heating, matlab you're heating and suddenly cooling. If you are making a cylinder, one end of the diameter may be smaller and other end of the diameter may be bigger. So the uniformity may not be there. Cracking. Cracking means between the layers, if they are not sticking together properly, then cracking is possible. Surface roughness, if the layers are not properly made. Delamination, again, it is the layer to layer separation. Dimensional error, if our during HTL file conversion, your model dimensions can be slightly affected. And contamination, if you are printing the material in the contaminated area, the dust can form and that can affect the one. So these are the defects that are possible in the 3D printer, which has to be avoided. So now, so far, we have talked about a basic understanding of the 3D printer, how a 3D printer established from nothing to something very big. When it is trying to become something very big, we also see what are the basics and fundamentals that are needed. So we will see some new techniques that have come in the 3D printer, which are very much new, and let's see them. First is material extrusion. This is nothing but FDM. You might all have seen. The first method is not a highly advanced method, but now what happened is that now a lot of new options started coming in material extrusion, that you can control through the nozzle. In fact, a new kind of innovations that can even come in the nozzle diameter. so that the fast at which the material printing can be controlled. As of now, nozzle diameter for a specific case is fixed. But if you there are certain systems that are coming up which can have a very different kind of nozzle diameter. So they are like some kind of new innovations that are coming. First method is a very basic method that is already existing, but the second method is something very much new. The second method is called wet photopolymerization, that comes under SLAR DLP. See, a liquid photopolymer resin is cured layer by layer and using UV lights and laser. So this is like SLA type. Okay, but in that SLA type, a new type called DLP, that is digital light processing techniques, are coming up, in which a projected lights are used towards specific directions in which your material can be cured. So these are very much useful for materials that are light sensitive, especially epoxy and acrylic. So wet photopolymerization in the DLP and SLA are coming up. And second thing is material jetting or polyjet. So what is happening? Similar to inkjet printing, what you are making the printing, here what is happening is a droplets of polymer or jet from the multiple nozzles and cooled by the UV light instantly. So when we see in a FDM, we are actually creating a layer by layer. The filament is heated and then they are deposited in a semi-solid format. But in material jetting, that is coming in a polyjet technique, a photo for polymer droplets which are in liquid format is sprayed using multiple nozzle, immediately cured by the UV light. So instantly solid liquid is converted into solid and layer by layer is created. Here, multiple materials and multiple colors are also possible. For example, if I want to print a blue color material in FDM, I have to buy blue color filament and the entire material will be blue. If in between color has to be different, I cannot do it in FDM. But in material jet in MJ, the new techniques have started coming up in which different kinds of colors are possible, different materials are also possible within the same designs. Okay, so the materials that are photo sensitive to UV lights are possible. And the fourth is like binder jetting or a BJ or the in short or 3DP. So what is happening in this kind of techniques is liquid binder is selectively deposited onto a powdered bed. So that liquid binder, it is binding the powders and solidifying the powder, and that makes the particle. See, the binder bonds, what they do is layer by layer powdered material is sprayed on the spray, and due to that spraying, your powdered particles are getting united. And then after making it, if you cure and sinter, the material gets into the shape. Especially the metal, ceramic, and sands we can able to make. So if you go back from the first method, that is the FDM, that is already there. Let's go back first and start understanding. The second is photopolymerization. So in which photopolymer resins is used, which are developing layer by layer using UV light. So first is the FDM method, second is wet photopolymerization, third is material jetting. Material jetting is nothing but we are making droplets of polymer and creating the component. And fourth is the binder jetting. So these are the latest advancement or different types of 3D printing that are coming up in markets. So liquid binder, as we saw now, the metals such as ceramic, sand, or metals, all are possible in this one. The fifth one is powdered bud fusion. So what is happening is this is one of the very industry significant category. You can write it down also, powdered bed fusion. So here what is happening, it is more or less equivalent to the previous method. Here powder is sprayed on a bed using a laser or electron beam. The powders are melts and they fuse together. so that layer by layer powder is sprayed and it is heated with the laser and the material melts and fuse together. There are subtypes which are already knowing: selective laser sintering, selective laser melting, and electron beam. The major advantage of recent is electron beam melting is also available, which does this powdered bed. So powdered bed is actually what we use in industries. Okay, the material that is in nylon, TPU, metals, titanium, aluminum, stainless steel, inconel, all are possible. And the sixth method that is coming is direct energy deposition. So what is happening? Powdered or wire feedstock is deposited through the nozzle, and it is much more similar to previous. The only difference is we are using a nozzle through which I am focusing a laser light. So since I am targeting a using a nozzle on a material, it is coming under the concept called directed energy deposition. But in previous case, a laser or a electron beam is sprayed on throughout the layer at a time. But here, a specific uh, target is used to direct the energy. So here, what is happening? So this has some other subtypes like laser engineered net shaping, wire arc additive manufacturing, electron beam techniques are the new kind of techniques that are coming up in the market. And seventh is the very recent one, that is sheet lamination. Here the sheets of material are stacked and bonded. Say layer by layer instead of making, already sheet material is available. So I can go to a company where the sheet metals are available at specific thickness. I can buy them. I can only manually keep one over the other. That is called a sheet lamination. And then I can stack them and bond them layer by layer. And then I can cut the shape, which means that layer by layer I pasted all the material and cutting the shape of it is what is called a sheet lamination. Here 3D printing is not needed. You have to manually keep the layer on top of it each other through some specific bond, and then using the laser you can cut it. Okay, so there are subtypes like a laminated object manufacturing or ultrasonic additive manufacturing are possible. The concepts that are possible under these techniques are paper, plastics, polymer, aluminum, titanium, and fossils. So now you need to understand one common knowledge or alertness, I can say. When there is a negative mindset of there is no more invention possible, then nothing would have got invented even now. When the telephone was invented for the first time, people thought they have achieved the ultimate product needed for rest of their life. But as soon as they started using, they understood that in order for somebody to call and answer you, you should be at home. If you are not at home, then the telephone may not be useful. So then people thought I need to carry the mobile with me. So they made a wireless, and slowly mobile and so much advancement has come. The same manner, when you start thinking about 3D printer, it might look like already completed product, but I'll tell you there are so much of developments and room for improvement is still there. The only thing what we have to do is you need to make sure that the gaps can be filled. For example, there are still 3D printed material. If you are using for structural application, you will have some gaps like porosity, some cracks are possible. As of now, there is no way to eliminate them, but there are ways to reduce them. But they are still existing. If you can able to develop a new method or new technique that can reduce those things, then they become a very much research idea. You can even suggest a method in which, yeah, in FDM process, how a new kind of materials can be printed. Now, one more advancement in the FDM is I have multiple nozzle printed, which means that at a time only I can print two different material in the product. First is like assume PLA and TPU. I can print one layer of PLA and certain number of layers on TPU. So my material or product will have multiple layers of different material depending on the need of the application.
So when all the different kind of techniques what we saw, there are improvements are always possible. Okay, so these are the seven improvements that we wanted to this. Next, we will be moving on to next we will be moving on to the AI. But before that, let me show you this particular slide where the summary of entire methods, whatever we discussed, and their positives and negatives are compared in the slides. Okay, so this once I give the slides, maybe you can refer. But now let's move on to the a very core of the advancement needed in additive manufacturing. See, artificial intelligence refers to the system that can analyze data, learn patterns, and make intelligent decisions, and often they're fast. What is not possible by the human brain is not possible even by artificial intelligence. The only thing what we wanted to understand is human brain is always superior. Whatever artificial intelligence we are developing are not so superior like a human brain. So you can think like this: the limitation of the thinking capacity of the human brain is limited by the capacity of the brain itself. How that limited brain can develop a technology which can be more intelligent than the brain itself. So if you want somebody to develop artificial, I personally believe it can be created by some system which has more intelligent than the human brain, then the AI will be more intelligent than the human. As of now, the AI may be faster than human. AI might have the thinking capacity, but AI can never replace the human brain in the functions. However, it can help you to solve your problems in a much easier and simpler manner. We will be seeing how it is possible in additive manufacturing techniques. See, the first and foremost additive manufacturing application of AI comes in design optimization. When I make a design, that is manually, I am putting my idea and creating a model. And now that model might satisfy my need, but it may not be the optimized model. So in design optimization, the AI plays a very major role. I'm literally telling you, if in design optimization, if you are not using AI, then there is no use of using AI for rest of the methods, because this is the fundamental place where AI can play a role. So AI plays a major role in design optimization. See, for example, I can share one small experience. What we do in my lab is we are developing a vibration isolator using a 3D printing technique. That's we have a polymer based FDM printer. Once the isolator is printed, we actually test them in our vibration shaker experiment setup to see how much vibration it reduces to the mass. By keeping some specific mass, we tested one. But our vibration isolator are not optimized one when we design initially. Then we optimize them by creating some kind of programs and some kind of limitations so that optimize the shapes. Then we go for the final printing. So this optimization is done by AI. In fact, the optimization techniques, if you take generally, it was existed even in 2004, because that's the time period where I was doing my BTech 2004 to 8. So that period also optimization technique was existed, but the AI was not so famous. AI is nothing but an optimization technique. What is optimization technique? I have a model. I know how my output will vary with respect to my input. Now I want to either minimize or maximize my output for a given input. If that one-on-one single input, single output problem, the optimization is very simple. You need to find the global minimum or global maximum as per your application, and boom, done. The complexity will come when you have a multiple input but single output, and you need to make sure the combination of the single inputs or multiple inputs that gives the highest possible output. The next level of complication comes in multiple input with multiple output also. So you need to find the various combinations of the inputs so that your output can be best possible from the given set of inputs. When multiple inputs and multiple outputs comes into play, human brain gets more overloaded. We will stop thinking because it's too much for the human brain to think. So we stop thinking. So for such places, AI plays a very role. So you program something and make it to optimize and boom, you will get optimization. And second is process monitor and control. See, when a 3D printer is printed, for example, for 8 hours, for 10 hours, sometime in one time our printer was printing the design for 15 hours also. Somebody has to sit next to the printer and always look at the printer. Why? When the 3D printer is printing, suddenly printer can behave abruptly, which is unpredictable in every possible manner. In that cases, what we need to do, we need to make sure that the product what we are printing and the design process what is happening within the given needed possible one. Okay, so that can be replaced by the AI. Now what I will do is instead of a human sitting and watching the 3D printed product for next 15 hours, I can put one AI that is monitoring my product. Like I will put one video camera that is seeing my 3D printed product and reporting to the operator how the printing is going on. If suddenly there is some abnormalities might come, then quickly I can be alerted. Once I get alert, then I can do something about it. For example, filament. The filament has to smoothly roll out of the filament roll and goes into the 3D printer. But there are times at which filament may not smoothly roll, it may get tangled in the roll. So that time I can go and simply untangle them so that it smoothly passes into 3D printer. Such kind of process monitoring, you can use AI. So one, the first foremost I said AI is design optimization. Again, I'm repeating, if you don't use AI for design optimization of your component for 3D printing, please don't use AI for rest of the methods because you missed the first most application of AI in 3D printing. Now the third most application what it might get. So you know all the steps what are needed. You know what is the advantage and negative disadvantage. So you have to understand you are going to reduce the disadvantage by incorporating AI to every disadvantage point so that the disadvantage can be reduced. The next disadvantage is defect detection. So first optimization, process control, and third is defect detection. If AI can identify and address that defect so that when you are actually making your defect can be reduced. See, there is a concept called digital twin. What is called digital twin? Say, if I am having one motor that is running in my company, then I will have the same model of the motor even in my computer program that will run like an actual model. If I'm using the real motor for 10 hours, I will also run my digital motor also for 10 hours. So when my digital motor shows some issue and the digital motor is made in such a manner, it will replicate the functions of the actual model. When my digital motor running for 15 hours or 10 hours started showing some error, most likely even in actual motor also that error have started showing. So what you created a twin, which means a lookalike of the model, but not in physical, but in digital mode. That is called digital twin. Digital twin technology is not a very new. It is there in last 5 years. It is already there. Okay, so you can simulate the 3D printed um, before even actually you print. You can simulate with the given process parameters and check if I proceed with the given 3D printer, whether my model will have defect or not, you can check it even before you actually build. If it is really possible of some error,
then you can actually rectify the process parameter until no error is available. So this kind of new simulations are possible in AI. So now these three things you understood. What is the fourth one that is possible? That is the material prediction. See, once a material is fabricated from 3D printed, then there is no control is that like undo. There is no undo. There it will be a filament. Once the filament is printed and converted into product, it is the product only. It can never again become a filament. So if you find that after 3D print, your material don't have enough strength, what you can do? You have to simply throw the object, print again with the improved parameters. But if you have AI, you can forecast after I print this shape, what would be the strength it can carry. That is what I'm calling it as material property forecast and performance. So now you can ask me material property means what? Because if I use polymer, if I use PLA, the material properties are same. But how the material properties are affected is the 3D printed material property. If I start saying the Young's modulus of the 3D printed material, the Young's modulus of a normal material of same type are not same. Because in 3D printed material, the layer thickness affects the strength. So the Young's modulus may or may not be larger than the actual material. Okay. So this kind of performance are possible with the AI. The next possible is the quality assurance. I know that, or even you know, you will definitely agree with me. When I finally make the product, I want the product to have highest quality possible. But how to make sure the process parameter what I use will finally yield me the highest possible parameter? I cannot fabricate and check and to see what kind of quality I will get, but rather I will use the AI to simulate and check what could be the quality it can give. So if you see from the first 4 or 5 technique in which AI advancements are made, it is used in design optimization, process monitoring and control, defect detection, material prediction, and quality assurance. The last advancement of AI that are used is supply chain production. What is supply chain production and planning? See, why focus only on the 3D printed object? See, there is a complete supply chain possible. Like if a customer is ordering a product, it has to be printed, then it has to be packed and sent to a customer. So the complete process of this can also be controlled by the AI. So now what is happening is when a customer gives order, AI intimates you start 3D printing, or AI is directly connected to 3D printer. As soon as the customer gives order and the design, it will be 3D printed. Once 3D printed, the human can be involved in post processing. As of now, post processing is not possible in automated. What is post processing? The 3D printed parts has to will have lot of supports. This support has to be removed manually, and we need to slightly smoothen or grinding to get a better surface finish, so that the product looks shiny and smooth. And then finally it can be packed and sent to the customer. So entire supply chain management can also be controlled by the AI. Okay, so these are the different advancements that are possible in additive manufacturing using the AI. Say, if you are a research person trying to do research on AI, I have a very general advice for the general audience. See, when you are trying to publish a research work and it gets published in a very good journal, in fact, I was actually listening some talk. I don't get full topic of what the previous topic, but I joined in last 2 minutes, so I understand you were all focusing on the journal publication. So I like to add one line which is in line with additive manufacturing and topic also. So when we are trying to publish a research on any field, even including additive manufacturing, so what happened is that general public read the material, they'll understand your finding, and they will understand what happens to the output when I change this kind of input. They learn and they don't repeat if it is a mistake you are trying to predict or if it is the best design you are proposing, they will directly use to make the product. But what is the final outcome? What you get? Nothing. Merely you get a citation of the person who try to publish more research in the same area. Other than that, there is no a special benefit of your research. So if you are going to do a research just because of advancement or finding something, I don't think personally it may not have a much benefit to you. You see, your research should be always oriented in developing a product. Why? If you finally develop a product, if the product is having a commercialization benefit, then that gives a very good returns for the time you spent on this research. So if your research is based on product rather than data, rather than on plots, rather than are finding relation between input and output, that's mathematical modeling. If your research is based on product, let me tell you, it can result in patent, and patent can be commercialized to a company so that you get a good commercial benefit and returns of the time spent. At the same time, whatever you are uh, uh, doing on the product development, definitely you will find some result that can also be published. When I am trying to find something on AI, on additive manufacturing, whatever advancement is made does not fully satisfy all the needs of AI. I have shown the defects. For example, let's go to the slides of the defects. So I discussed the defects. I think this is a slide that tells the defect. Even now, all the defects are not completely solved by anybody yet. So you take these defects and try to make some program or a product that will not create this defect. For example, cracking. So you develop a AI model that can predict the crack before even the crack is actually created with 3D printing and intimate to the user. So by this, you can understand the cooling rate needed for the AI. The people have made the AI, for example, if I'm buying on 3D printer, when I'm starting a 3D print, it will show the time taken to print. It is also simplest form of AI that tells how much time it will take, right? But this is a small kind of advancements are possible. All the defects, whatever it is there, are still there majorly in all the current 3D printing techniques. So when you want to develop an AI, try to actually solve this problem and make the AI as one software package that can be commercialized to a 3D printer manufacturer. So what happens along the process of making the AI software, you also get a commercial benefit and the content can also be published. Otherwise, the time spent on finding out the data is directly given to the reader without any personal benefit or returns of your time spent. The reader reads the paper and happily goes forward and does. Of course, you get a citation. Citation also adds value, but in paper it adds value. Physically it don't add much value to you. Only product can physically add a value to you. So with well, that is the one point I wanted to add with respect to the kind of research you wanted to do. So these are the major topics which I wanted to share with the viewers on how advancements in additive manufacturing are made and what kind of future researches are still possible in the additive manufacturing techniques. Okay, so with that, I think I would like to finish my presentation. Thank you very much. And here my mail ID is given. Here I like to add one point. NIT Rourkela, Dr. Bhargav already knows. He is from my lab.
So we are having a lab called Materials and Wave Propagation Lab, where our basic fundamental is we are having a lot of 3D printers and we print lot of materials. And if you have any requirement in 3D print, or if you want to know further about 3D printers, or if you want to print a specific design for your research, please don't feel shy. You can directly mail me. We have a different kinds of 3D printer, but all are polymer based, not on metal. NIT Rourkela still in the process of procuring metal based. You can write a mail to me. I will definitely assist you in helping you and making a 3D printer. I can even suggest you some new changes you can make to print efficiently. Okay. So with that, I thank you guys for this opportunity. And if you have any discussions on this, I am open to the question. Thank you.
Thank you very much, sir. Dear participants, if you thank you very much, sir. Dear participants, if you have any queries or questions, please feel free to ask. Guys, so I think there are no questions, sir. Actually, they're all appreciating the presentation. I hope you can see that.
Yeah. Thank you. I think when there is no questions, it only means two things which you already know. Either they understood fully or they didn't understand at all. But I hope on the positive side that you understood majorly. Of course, if you have any assistance or help, you can always mail me back. Thank you.
Yes, sir. So, sir, thank you, sir. So there's a question, I think.
Can we use aluminum foam as a material for additive manufacturing? As of now, that is not yet come at all. So you can use aluminum material, but aluminum foam, I don't. As of what I know, is not yet come yet. It might come in future, but not yet come.
Okay, then if there are no questions, sir, we extend our heartfelt gratitude for delivering an insightful session, sir. We are sincerely grateful and appreciate your time and effort that you have put in for sharing your expertise with us, sir. Thank you, sir. Thank you once again. And I hope we will meet again for one more session on Thursday, I think. Thank you, sir. Thanks for joining.
Yes. Thank you, Dr. Bhairav, and thank you, QS College, for this opportunity. I am excited to meet you again on new topic. Thank you very much. Thank you.
Thanks a lot, sir. Thank you. Dear participants, with this, we have come to a conclusion for today's program. So we'll meet you again at 6 p.m. tomorrow. Within few minutes of time, we'll send the feedback link as well as attendance link. Please feel free to fill that form and register your attendance. Attendance is very mandatory for this program. I request everyone to join tomorrow at 6 o'clock. Thank you, guys. Have a good day.